Energy again. All right, so this time we're going to talk about what rules energy plays by, because we know as physicists, as scientists, that nature plays by a set of rules, and we've discovered what those rules are. And lastly, where does energy come from and where does it go? If you have a good understanding of this, you can understand anything for the rest of this marking period, okay, or the rest of this project at least. All right, so what rules does energy play by? Number one, there's two, but number one is the law of conservation of energy. Now, what this says is that in any transformation of energy from one form to another, the total quantity of energy remains unchanged. So when you're going from one form of energy to another, the total energy remains unchanged. It's the same. So the energy before equals the energy after. Let me word that another way. Energy cannot be created or destroyed, but it can change form. That's key. So, in other words, energy cannot just be created. It doesn't just come from anywhere, and it doesn't just go or disappear. But it does change form from one form to another. That's the idea, okay? You can go from electrical to thermal to radiant to chemical to potential to electrical. You can change form, okay, and some gets wasted, but it doesn't just disappear and go away. Total energy stays the same. That's law of conservation of energy. The second law is called the second law of thermodynamics. Okay? There is a first law, but don't worry about that. What this one is saying is that in all energy changes, whenever you're converting from one energy to another, the potential energy of the final state will be less than that of the initial state. The bells are off today. What that does mean is that the useful energy, there is some useful energy that is always lost. The total energy stays the same, but the energy, some energy somehow got lost and gone somewhere else. Okay? Let's see. In other words, lost energy is usually energy that has been converted to heat. It could be noise or some other sort of thing. For example, when I drop my pen, okay, the pen hits the desk, and the energy that it had as it was moving gets transferred to the desk. Now, technically, it moves the molecules in the desk, which heats them up, right? And it makes noise that you hear. So the energy gets turned into some other form. If you're playing on a seesaw, okay, there's some friction there, and that friction turns some of the energy that you're putting in as heat. So the application here is that it's impossible to make heat flow from something that is hot to something that is cold. That's more for thermodynamics, but the idea is that you can't just create energy from somewhere. So it's actually quite similar to that first law. All right, so second question. Where does energy come from and where does it go? Now, according to the law of conservation of energy, energy has to come from somewhere. It doesn't just magically appear, okay? And it doesn't magically disappear. So energy has to come from a source and then be changed into another form. So another way of looking at that is you have a source of energy, okay? You have a transformation, okay, and it turns into another form of energy. Okay? The source could be coal, it could be wind, it could be the sun, it could be a battery. There's some source of energy. So it's basically, it's potential energy and it turns into some other form. Could be more potential, could be other kinetic. Okay? All right, let's try some examples, and these examples are ones that you're going to have to do in your class tomorrow. So here's the key. We have a light bulb, right? Now, where does the energy come from and where does it go? Well, first of all, the energy source for this is electricity. Okay? Okay? Electricity or electrical energy. Okay? That's because you have electrons flowing. Okay? So you have electricity. Now, the electrons are flowing, and they actually flow up. They flow up this little bit right here. It's the filament. And they continue to go across the little coil filament here, and then it goes down, and the electrons continue to flow. Thing is, they hit friction here in the metal. Now, in that metal actually heats up, so it turns into thermal energy. Okay? Thermal, wow, my handwriting is terrible. Thermal energy that's in that coil, okay? The molecules in that metal are moving really, 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 really fast, and they heat up, and eventually they heat up to the point where they become glowing, and that's the radiant energy, okay? The light that you see. Okay, wow, terrible. But that's what you get. Now, if we want to go back another step, we could say, where did the electricity come from? Well, it probably came from, don't just say the wall, coal, or maybe nuclear, or maybe wind. Somehow, something made electricity to get it to your house, which then turned into thermal energy and turned into radiant energy. Okay? That is an energy flow diagram. One thing I didn't show in here yet is that some of the energy gets lost as wasted energy. Some of it gets lost, especially here. The thermal energy, some of it turns into light, but a lot of it gets turned into heat. That's why an old form incandescent light bulb is very wasteful, because it makes a lot of heat. Those new little swirly ones, not so much new anymore, but those are more efficient. One reason is because they don't make as much heat. They get more light with less heat. That's why they're more efficient. They don't waste as much energy. All right, so that's the energy diagram for a light bulb. Okay? Let's try another one. Let's do a flashlight. All right? With a flashlight, it's slightly different, because what you're starting with, okay, is you start with what we call chemical, that should be an M, chemical potential energy. Okay? And that is the battery. Okay? The battery has that energy. Right? Now that, once you make the electrical connection, turns into electrical energy. Okay? And that electrical energy, if it's an incandescent flashlight, gets turned into thermal energy, which then gets turned, because its heat gets hot enough, into radiant energy. Okay? That's basically what's going on there. But what if I have, forgot the wasted heat, or the wasted energy. Not all that energy actually goes through. Some of the electrical energy gets lost and doesn't turn into heat, and some of the heat just gets wasted and gets absorbed by the rest of the flashlight, and the flashlight heats up, but not all of it turns into light. Now, what's another part of this? What if I did something different? What if I had something like this? A hand generator flashlight. A hand generator flashlight. Okay? There's something different going on there. Okay? In that case, we got to make a couple changes. It's not chemical potential energy as in a battery. No. What's actually happening is we have a different source. We have basically my, mechanical kinetic energy. Okay? That's me moving. That energy, that movement, gets turned into electromagnetic energy. Okay? Because there's a whole bunch of like magnets and wires and stuff in here. And see, that electromagnetic energy then gets turned into electrical energy, which then gets turned into thermal or radiant. Okay, technically these are LEDs, so it's not thermal, but ignore that. Imagine they're actual incandescent. Okay? But that's the idea, that stuff changes. Now, we could go even further back. Now, what gave me the mechanical kinetic energy to do that? My food, right? So that would be chemical potential energy. Okay, that would be food. And what gave me the energy to do that? Well, where does the energy from food come from? Well, sugars or carbohydrates or other things. Where does all that come from? It comes from plants, which get their energy from the sun, which is, surprisingly, or not surprisingly, radiant energy. And it's kind of interesting how the sun's radiant energy helped fuel my food, the things that grew from my food, which I then used to move stuff, which then moved some electromagnets around, which created electricity, which created thermal energy, which went right back to light. Okay? So, if you remember stuff, remember, energy can't just